Let's look at simple harmonic motion. But first, let's look at periodic motion. What is a periodic motion? I want us to note that a periodic motion is a motion which repeats itself in equal intervals of time. So any motion that repeats itself in equal interval of time is known as periodic motion. Okay, that is for periodic motion. Now, if you look at the diagrams on your screen, on the first diagram right here, you can see that this object is moving in a periodic motion. As you can see, this is the first one. 1, 2, 3. As you can see, in these 3 instances, the motion is being repeated. As you can see, 1, 2, the same, 3. All right, so this is called a periodic motion. In the second diagram right here, you can see that the object moves straight, then up, it moves constant, then come down, again, goes up, it moves in a straight line, then comes down. This is a periodic motion. When an object or when a motion is repeating itself in equal intervals, we are saying that that motion is a periodic motion. All right, and please, you must note that the displacement of a particle in periodic motion can be expressed in a sine or a cosine functions. So in writing, I'm saying that the displacement of a particle in periodic motion can be expressed in terms of cosine and sine functions. I'll show us the equations in the next slides. So this is the concept behind what? Periodic motion. That's 1. 2, I'll show us a type of periodic motion, which is called oscillatory motion. Now, if a particle in periodic motion is moving back and forth or is moving to and fro over the same path, we are saying that that motion is oscillatory or is vibratory motion. So I'm saying that when a motion or a particle in periodic motion is moving back and forth, in bracket, let's say to and fro, all right, over the same path, all right, that particle is said to be in oscillatory or vibratory motion. All right, so that is the concept, or that is an example of what? A periodic motion. They are called oscillatory or vibratory motion. It's when a particle is moving back and forth, or to and fro. All right, we are saying that such an object is in periodic motion. I'll give us some examples of oscillatory motion. The first one I'll give to us right here is a circular motion. All right, a circular motion. A circular motion is an example of periodic motion because the object is moving around the circular path. It's moving around the circular path. All right, That is an oscillatory motion. Also, we have the motion of a pendulum. The motion of a pendulum. All right? So a pendulum makes an oscillatory what? Motion. Also, we have the motion of a violin string. That is also an example of an oscillatory motion. We also have the motion of a spring fixed at one end. The motion of a spring fixed at one end. All these are some examples of oscillatory motion. All right, so let's look at the characteristics of periodic motion. The first features that we note is that a periodic motion has an amplitude. The first characteristics, the first one is amplitude. It has an amplitude. Now, what is amplitude? Amplitude is the maximum displacement of vibrations of a vibration of a body from the point of what? Equilibrium. From the position of equilibrium. All right, and please note that it is measured in meters. All right, now from this diagram right here, the amplitude is from this straight line to this point. Here is our amplitude. All right, why this straight line is called the equilibrium position, is the equilibrium position. All right, so the amplitude is the point of this position of equilibrium to the peak or to the trough. This is called the amplitude. It can be positive or it can be what? Negative. All right, so the amplitude is the maximum displacement of a vibrating body from the position of what? Equilibrium. That is the first characteristics of harmonic motion. The second one is called the time period. The second one is called the time period. Number two is the time period. This is the second characteristics of harmonic what? Motion. It is the smallest interval of time after which the motion is repeated. Remember that in periodic motion, the motion is repeated in equal interval of time. So that smallest interval after which the motion repeats itself is known as what? Period. So I'm saying that it is the smallest interval of time after which the motion is repeated. Is what? Repeated. All right, and please note that it is measured in seconds. It is measured in seconds, and we have an equation for time period. It is given us, the symbol is T. All right, it's giving us 2 pi over W. And please note that this W is not your angular speed. It is called the angular frequency. So the W here is called the angular frequency. So please don't mistake this W for angular speed. It is the angular what? Frequency. So please note that for amplitude, the symbol is A. All right. For time period, the symbol is capital T. Let's look at the third characteristic of friction. It's known as frequency. Frequency is the third characteristics of friction, of harmonic motion. Sorry. We have number 3, frequency. All right. Now, what is frequency? Frequency is the number of cycles of vibrations, is the number of cycles of vibrations completed in 1 second. That is for frequency. The symbol we use for frequency is capital F. For frequency, the symbol we use is capital F for frequency. All right. So guys, I want us to note that frequency and time, or frequency and time period, are related by the formula F equal to 1 over T. All right. This T is a time period. Now, from this, we can derive an equation for frequency. I know that my time period is what? 2 pi over angular frequency. So therefore, I can say that frequency is equal to 1 over 2 pi over angular frequency. Look at this very carefully. I can evaluate further. I can say it's 1 divided by 2 pi over angular frequency. In maths, we can change this to times. It becomes 1 times. When I change this to times, I have to flip my right hand side. It becomes omega over 2 pi. So therefore, I can say that frequency is equal to 1 times omega is our omega, which is the angular frequency, over 2 pi. So here is a formula we can use to solve for frequency as it relates to harmonic motion. All right. So let's look at simple harmonic motion. Very interesting. Simple harmonic motion. Now, I'll start with a first point here, that a particle is in harmonic motion. If you don't mind, harmonic motion for short is written as SHM. So a particle is in harmonic motion, all right, if its acceleration along a line is directly proportional to its displacement along that line from a fixed point on the line. So this is the definition for simple harmonic motion. All right. So we are saying that if an object or a particle is in harmonic motion, we are saying that its acceleration must be directly proportional to its displacement along the same line. All right. And that's the first point you must note. Point 2 is that I want us to note again that simple harmonic motion is an example of oscillatory motion. I'm saying that simple harmonic motion is a type of oscillatory motion. Very, very important. We must note this. So simple harmonic motion is a type of oscillatory motion in which the displacement of the particle from the origin is given as shown below. Now, I'm giving us an equation that we use for simple harmonic motion. Okay, now the equation that we have for displacement as it relates to simple harmonic motion is given as y as a function of time, y a function of time is equal to the a sine, open brackets, angular frequency times time plus the phase angle. This is the displacement of a particle in a simple harmonic motion. And please, I want us to note that when displacement is a sinusoidal function of time, it is called a simple harmonic motion. Note, where displacement is a sinusoidal function of time, it is called simple harmonic motion. So please guys, we are to note these very important points. Now, when I say sinusoidal, it means that it is a sine function. I repeat that. When I say sinusoidal, it means that it is a sine function and the graph looks like this. Look at this. All right. So here is an example of what? A sinusoidal function. It means that it is it's a sine graph. It's a sine graph. Okay. Now, I want to explain what these terms represent. So please look at your screen very well. Let me explain what these terms in this equation represent. Let me show us what each of those terms represent. Okay, we have y, function of time. So our y is displacement with respect to time. Okay, our a is the amplitude. Okay, our a is the amplitude. The w there is the angular frequency. All right, and the phi, what you are seeing there as phi, the phi is known as the phase constant. So the phi is the phase constant. All right, so the phi is the phase constant. And please, I want us to also note that everything you see right here is called the phase angle. So I'm saying that omega t plus the phase constant is known as what? The phase angle. This is the phase angle. All right? It's measured in radians. Please note that the phase angle is measured in radians. I repeat that. The phase angle is measured in radians. We are saying here that omega t plus phi is a phase angle and it is measured in radians. Please don't forget that this angle here is measured in radians. What does that mean? It means that when we are solving these questions, when we are looking for sine of whatever is here, we have to set our calculators in radians. So if your calculator is in DEG, that is degrees, it will give you the wrong answer. So when you are solving this question, your calculator must be set to what? RAD, because this phase angle is measured in what? Radians.